Welcome to LR3-1. In this lesson, you will learn how to identify the hypothesis and conclusion of a statement, be able to write conditional, converse, and biconditional statements, be able to draw a Venn diagram, and identify counterexamples. In this unit, we are stepping away slightly from some of the arithmetic math that we are used to. We're going to be taking ideas that we believe are true and proving them. Or we're going to be taking some math and we're going to be proving that it is correct. Mathematicians, engineers, lawyers do this all of the time in their day-to-day life. We're going to learn how to make a case logically. Okay, we're going to list out all reasons and explain why or prove why it is true. We are going to be learning this and doing this with math. In this first lesson, we're really going to be focusing on a lot of the vocabulary that we will be using throughout this unit. All right, we are going to start with a statement that says every creature who drinks water will die. We're going to use this statement to help us understand some of the vocabulary. We're going to use this as an example. Yes, the statement is a bit over dramatic, but it is technically true. We're going to take our statement and we're actually going to write it as a conditional statement. So we're going to use the statement above and we're going to use words if and then. So if a creature drinks water, comma, then it will die. The if part is called the hypothesis. Okay, so our hypothesis in this example, a creature drinks water. We don't need to write out the if, but the hypothesis is that first part right after the word if. Then part is called the conclusion. So then it will die. Again, don't need to include the word then. It will die is the conclusion part. Now, conclusion you can think of just like in language arts. It's at the end of the statement. The hypothesis, you can consider it, kind of like in science, how we consider it's the prediction. The hypothesis is the first part. A counterexample then is anything that proves that the statement is false. And we only need one. So if I could find one creature that drinks water and never, ever, ever dies, that would be considered a counterexample. In this case, we don't have a counterexample because there are no creatures who drink water and will never die. To give you an example of this, let's say I had a conditional statement that says, if you are a math teacher, you teach at Minnetonka Public Schools. All I need to do is find one example of when that is not true, and that will be a counterexample. Another example, if I were to say all babies like sweet potatoes, I just need to find one example where that's false, which would be my daughter, who does not like sweet potatoes. So that would make that false. That would be the counterexample. For a converse statement, all we do is we swap the hypothesis and the conclusion. So, for example, if A, then B would become our if and then stay. So it would become if B, then A. Going back to our example of if a creature drinks water, then it will die. The converse statement would be if a creature dies, then it drank water. And yes, there are some language things that we need to switch. We switched drank to the past. It is important to note that although the conditional statement might be true and is true, the converse statement might not always be true. In this case, it's not necessarily true that if a creature dies, it drank water. There could be a creature who never ever drank water and died from dehydration. Just because the conditional statement is true does not necessarily mean the converse is true. Now we have biconditional statements. Those only work when both the conditional and the converse are true. So instead of saying if A then B, it becomes A if and only if B, or B if and only if A. We get rid of the if and the then and change it to if and only if. So using our example, we could say a creature dies if and only if it drank water. Or we could write it as a creature drank water if and only if it dies. All right, let's talk about Venn diagrams. You've maybe used them, seen them in language arts, in social studies. They were actually originally invented by this man here, John Venn, and for mathematical purposes. John was a mathematician who was really, really into diagrams and into logic. And what he did is he created a diagram representing mathematical or logical sets using circles to show where and how things relate. You are used to seeing Venn diagrams that look something like this, where they have their own circles, but then there's a part that overlaps. Could also have a Venn diagram where we have one set and another one that's inside of that set. I could also have two sets that are completely separate and don't overlap at all. Let's take some time to look at some examples. So number one, if you finish dinner, then you can have dessert. This is our conditional statement. Our hypothesis is the first part, you finish dinner. The conclusion is after the then, which is you can have dessert. The converse of this would be flipping those. So it would say, if you have dessert, comma, then you finished dinner. And yes, there are some English things that, like, for example, finished, and you need to change it to past tense, and that's okay. And with this converse, we can kind of think about, is that always true? Has there ever been a time where you got dessert and you maybe didn't finish dinner? Maybe you didn't finish all your vegetables. Maybe you had ice cream for dinner because it was your birthday, or whatever it might be. So if we look at the Venn diagram, we can have all the times that we ate dinner, and then we're going to have the times that we had dessert. And yes, there's going to be times that we had dessert after we ate dinner. However, there's going to be this piece here, which is outside of that circle, which represents maybe when you didn't finish dinner, when you didn't eat all your vegetables, but you still got to have dessert. Since the conditional and converse are not both necessarily true, we are not going to have a biconditional, and we're going to look for a counterexample. So a counterexample could be that parents gave in and gave you dessert anyways. It could maybe be that you had a babysitter and you convinced them that you didn't need to finish your vegetables. Maybe it's your birthday, whatever it might be, those are our counterexamples. Our second example says, if you study for the test, then you will do well. Our hypothesis is you study for the test. The conclusion is you will do well. My converse flips those two. So if you did well, then you studied for the test. Got my circle of all the tests I've ever taken that I've studied for. And then I've got all the times that I did well. Notice that there's a little piece here that represents the times that I did well, but maybe didn't study and got lucky. So in this case, we don't have a biconditional, and we're going to have a counterexample. Maybe the test was really easy. You didn't study and you did really well, and the test was super easy. That could be a counterexample. Example number 3 says, if you have a driver's license, then you can legally drive. My hypothesis is you have a driver's license. Then my conclusion is you can legally drive. I'm going to flip those two for my converse. So if you can legally drive, then you have a driver's license. Here's our Venn diagram. So here are all who can legally drive. And here are all who have a driver's license. Notice it's one circle. They are both true. You must have both, which means there are no counterexamples, and we can write a biconditional statement. So we'll write it as you can legally drive if and only if you have a driver's license. Notice we changed the if and the then, and the glue that sticks these two parts together in a biconditional is the if and only if. So this is one way to write it. The other way to write it would be you have a driver's license if and only if you can legally drive. You do not have to write both these biconditional statements. I'm just showing you that either way works for the biconditional. Example number 5 says, if a polygon is equilateral and equiangular, then it is a regular polygon. So our hypothesis is a polygon is equilateral and equiangular. The conclusion is it is a regular polygon. Our converse statement would be if it is a regular polygon, then it is equilateral and equiangular. For my Venn diagram, I have all of the polygons that are equilateral and equiangular. And then I have all of my regular polygons, and notice they overlap completely. This means that there are no counterexamples. There's no case where they are both not true. What that means is that we can write our biconditional. Again, if the converse is true and the conditional is true, then I write a biconditional. There are two ways to write this biconditional. One way is a polygon is equilateral and equiangular if and only if it is a regular polygon. That's one way to write it. The other way to write it would be to say it is a regular polygon if and only if it is equilateral and equiangular. Our final example looks at a real-world example of a business. Businesses use this all the time. So for example, Target, you've heard the saying, expect more, pay less. That is their slogan. We can write a conditional statement for this, which says, if you expect more and pay less, then you shop at Target. So the hypothesis from this is the first part, which is you expect more and pay less. The conclusion would be you shopped at Target. We can flip this around and write its converse, which would say if you shop at Target, you expect more and pay less. Then you expect more and pay less. So if we think about this, we want to think, are we going to have a biconditional or have a counterexample? In this case, we are going to have a counterexample if we can come up with any time where we got a better deal at somewhere other than at Target. Maybe at the gas station, maybe at Walmart, maybe at another store, you got a better deal. That would mean that we wouldn't have a biconditional here, and we would have to write a counterexample. So maybe at a gas station, or at Walmart, or at Aldi, or at another store. This would prove that it's truly false because of these counterexamples. Again, we only need one counterexample. You could also look at a counterexample saying you are somebody who shops at Target, but you don't expect to pay less. Here are some fun Venn diagrams with some fun jokes. Go ahead and take some time to do the practice problems. Feel free to rewatch this video at any time.